All right, let's jump right into this. Welcome to this explainer, where we're going to literally build the ultimate physics toolkit. Now, have you ever wondered how scientists all over the globe, speaking dozens of different languages, can perfectly understand each other's research? Well, it's because they use a universal language. Today, we're going to master the foundational grammar of that language, the core rules of measurement. Because honestly, without these rules, physics is just a random jumble of numbers. But with them, we can decode the very fabric of the universe. So here is our roadmap for today. We're going to hit the international system, then move right into precision and significant figures. From there, we'll tackle math with significant figures, explore the dimensions of physical quantities, and wrap the whole thing up with dimensional analysis in action. Part 1. The international system, or SI. The vocabulary. Okay, before we can measure the world around us, we have to agree on exactly what we're measuring with. To build this vocabulary, we really need to understand the difference between base and derived units. Think of base units like the alphabet. They're independent, fundamental units that stand completely on their own. Derived units, on the other hand, are like the words we build from that alphabet. They're just combinations of base units created by multiplying or dividing them to describe much more complex stuff, like velocity or force. And here is that entire alphabet for the physical world. It's just 7 fundamental SI-based quantities. You've got length, mass, time, electric current, and a few others like temperature and luminous intensity. That's it. Every single measurement in the universe, whether it's the speed of a rocket or the density of a dying star, can be broken down and expressed as combinations of just these 7 base units. It's actually wonderfully elegant when you think about it. Moving on to part 2. Precision and significant figures, the grammar of measurement. So if units are our vocabulary, significant figures are the strict grammar that keeps our data honest. Have you ever wondered if a bathroom scale or a lab tool is, slightly lying to you? The truth is, every measurement has some built-in uncertainty depending on the instrument we use. Significant figures include all the digits we know for sure, plus the very first uncertain one. The tricky part is knowing which digits actually count, especially when we start throwing zeros into the mix. So let's lock in the golden rules. First up, all non-zero digits are always significant. No exceptions. Second, zeros sandwiched right between non-zeros, they count for sure. Third, leading zeros, those guys to the left of the first non-zero digit, they never count. They're just there to locate the decimal. And finally, trailing zeros at the very end of a number only count if there is a decimal point somewhere in that number. Let's actually put this into practice to make it concrete. Take the number 0.002308. So how many significant figures are we looking at here? Well, applying our rules, those leading zeros before the 2 don't count at all. They're just placeholders. The digits 2, 3, and 8 are non-zeros, so boom, they count. And what about that 0 sandwiched right in the middle of the 3 and the 8? It absolutely counts too. So this specific measurement gives us exactly 4 significant figures. Now this brings us to a massive trap that is so easy to fall into: changing units. Say you measure a length as exactly 4.70 meters. Because of that decimate point, those trailing zeros are significant, meaning you have 4 significant figures. Great. But what if you convert that to millimeters? You'd write 4,700 millimeters. Well, suddenly there's no decimal. And according to our rules, it looks like you only have 2 significant figures. You just lost your precision. This exact ambiguity is why scientific notation is the ultimate fix. By writing it as 4.70 times 10 to the power of 3 millimeters, you perfectly preserve your 4 significant figures while changing the units. Zero confusion. Just pure, honest precision. Part 3. Math with significant figures. Honest arithmetic. It's a foundational rule of science that a calculated result can never, ever be more accurate than the original measurements it's based on. We have to do honest arithmetic, and we handle this with 2 distinct rules, depending entirely on the kind of math we're doing. When you're multiplying or dividing, your final result can only have as many significant figures as the original number that had the least significant figures. But, and honestly, this is where so many people get tripped up, when you're adding or subtracting, you don't look at significant figures at all. Instead, your final result has to keep the same number of decimal places as the number with the least decimal places. It's a subtle shift, but it's totally critical to ensure we don't accidentally overstate how precise we are. Now, inevitably, when we cut down our final answers to fit these rules, we're gonna have to round. And the rule for rounding a number that ends in exactly 5 is actually fascinating. We all know if the digit to drop is more than 5, you round up. Less than 5, you round down. But what if it is exactly 5? By convention, if the preceding digit is even, you just drop the 5, leave it alone. But if it's odd, you raise it by 1. So, for example, 2.745 rounds to 2.74, while 2.735 also rounds up to 2.74. Why do we do this? Well, it prevents statistical bias across really large data sets, making sure we don't accidentally inflate our numbers by always rounding a perfect 5 up. It is just an incredibly clever way to keep our data balanced. Part 4. Dimensions of physical quantities. Abstracting the units. All right, this is where things get really cool. This is where we stop caring about whether you measured something in meters or feet or miles, and we just care about the fundamental nature of the measurement itself. We describe this core nature using a dimensional formula. Basically, this is an expression showing how base quantities represent a physical quantity, and we usually use brackets for mass, length, and time. Think of it as the underlying DNA of a physical quantity. For instance, speed, or velocity, is always, fundamentally, a length divided by a time. So its dimensional formula has 0 dimensions in mass, 1 in length, and -1 in time. And finally, Part 5, Dimensional Analysis in Action, the Physics Cheat Code. I seriously like to call this the physics cheat code because it lets us test equations and even invent brand new ones based on one simple rule, the principle of homogeneity. Basically, you can only add, subtract, or equate quantities that have the exact same dimensions. I mean, you can't add a mass to a velocity, right? It just doesn't make sense. So let's test this cheat code out right now. Here's a direct challenge for us. Is the famous kinetic energy equation, K equals 1/2 mv squared, actually dimensionally correct? Let's break it down and see. Okay, first, we look at the left side. Energy. Energy has its own specific dimensions of mass, length squared, and time to the -2. Now let's check the right side. That fraction, the 1/2, it's just a number. It has no dimensions, so we toss it out completely. We take our dimension for mass and multiply it by our dimension for velocity squared. When we combine those together, the mass, length, and time dimensions perfectly match the left side. The equation is dimensionally sound. It works! But honestly, just checking math is only the beginning. Dimensional analysis can actually help us deduce brand new formulas from scratch. Imagine a simple pendulum swinging back and forth. Let's make a guess that the time period of one full swing depends on 3 things: the length of the string, the mass of the bob at the end, and the acceleration due to gravity. How on earth do we turn that guess into a real, usable formula? Here's the magic trick of algebra. We set up an equation with our variables, but we raise them to unknown powers. Then, we look entirely at the dimensions. Because the left side of our equation is just time, meaning it has absolutely 0 mass and 0 length, the powers on the right side have to balance out to 0 for mass and length. When we balance those dimensions, we discover something wild. The mass dimension cancels out completely. A pendulum's weight doesn't even matter. By solving for the remaining dimensions, the math reveals the exact formula. Period equals a constant times the square root of length over gravity. Boom! We literally just derived a law of physics out of thin air. Now, of course, there is a catch. As incredibly powerful as this tool is, it does have its limits. Notice in that pendulum formula we just deduced, we had an unknown constant K. Dimensional analysis cannot tell us the exact numerical value of dimensional constants. We'd only find that out by running actual physical experiments in a lab. It also can't distinguish between 2 entirely different physical quantities if they happen to share the exact same dimensions. Our source material actually sums this up with a really brilliant quote to keep in mind. A dimensionally correct equation need not be actually exact, but a dimensionally wrong equation must be wrong. Dimensional consistency doesn't guarantee your physics is absolutely flawless, but it is the ultimate BS detector. If the dimensions don't match up, your equation is fundamentally broken. No questions asked. So, there you have it. You now understand the base vocabulary of the SI system, the strict grammar of significant figures to keep your math perfectly honest, and the sheer power of dimensional analysis to check and even deduce the fundamental laws of motion. Now that you're armed with the ultimate physics toolkit, what hidden rules of the universe will you decode next? Keep questioning, keep analyzing, and I will catch you on the next explainer.